Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters for making this video possible, and we'd also greatly appreciate if you consider supporting us as well, so please check the link in the description for more details. My name is Sava, and today we're going to investigate approximate entropy and its application for detecting dependencies and deterministic chaotic patterns in financial time series. And as an example, we've got a quite short and simple series of S&P 500 returns, just 41 returns. It's just because of the computational intensivity that the approximate entropy test requires. This can easily be replicated for larger samples. It's just that the tables that you'll need to calculate would be quite huge. So just for the easiness of it, just to be able to visualize everything quite simply, we just stick with a quite short sample. This also illustrates how powerful the approximate entropy test can be even in small samples, and that's the whole purpose of it. It has been first devised in biomedicine or in natural sciences more broadly to detect regularities in binary signals, so zeros, ones, that type of stuff, but it has been more and more actively applied in finance to check whether financial time series like returns of assets exhibit some nonlinear dependence. And in that case, and also due to its inherent logic, it's quite similar to the BDSL test that we have investigated in one of the previous videos. So please check this video out later if you are interested in the BDSL test. However, now let's investigate the approximate entropy test. The logic of approximate entropy dwells quite heavily on information theory and the measurement of the amount of information that each new observation releases to the observer. And we can compare the amount of information, or at least approximate that, that one additional observation of our series releases to us, and compare it to the amount of information that we would have obtained from a purely independent or random series. For example, a coin toss of a fair coin. And it is quite commonly known that the entropy of a fair coin toss, which is 50-50 heads and tails, is 1 bit. Or if we do a logarithmic entropy, that would be log 2. Because you have no presupposition what is more likely before the toss happens. Is it a head? Is it a tail? And we can apply the same logic to stock returns and code them as zeros and ones regarding their particular patterns. And here the logic of distances and distances between observations or vectors of observations more broadly is what is relevant. So first of all, let's calculate the total number of observations that we have in our sample, and we kind of already know that it is 41, but just for good measure, yeah, it's indeed 41. And then we need to specify the parameter s. S is an integer that basically corresponds to how many states we observe in our signal. And again, as I already mentioned, most commonly it is a binary signal that we're interested in, so a signal of zeros or ones. So there are two realizations of a signal we would code. And that is quite universal to financial applications and even applications in natural sciences. However, if you were testing, for example, the fairness or independence of dice tosses, then S would be equal to 6. You would have ones, twos, threes, and so on and so forth up to 6. However, we try to emulate our stock returns as coin tosses, so we'll stick with S equal to 2. And this makes calculations much simpler. And first of all, we'll have to calculate the distances between all potential pairs of our observations, including the double counting, so basically including the distances between observations with themselves. And this is what distinguishes approximate entropy from other types of entropy measurements like sample entropy, for example, that try to avoid double counting the observations. But for approximate entropy, let's just stick with the simplest case and just calculate pairwise distances between returns. That would be quite important to estimate our threshold distance parameter r that we'll then use to convert our continuous variable, that is return or distance between returns, into binary signal that then will use to calculate our entropy. So first of all, we can just use the absolute value of the difference between two index functions. So we refer to just the whole array of our S&P 500 returns and lock it row and column wise. And for our indices, we have got numbers from 1 to 41 conveniently tabulated here in the column and in the row. So we first refer to the element in column K, and then we subtract the same index function, but instead of referring to column locked K2, we refer to row locked L1. And we can enforce this formula, and using Ctrl R and double left click, calculate distances between all potential pairs of returns. And here we see that the diagonal constitutes of just zeros, because the distance between the return and exactly the same return is 0. That's no surprises. And we have got also positive distances between different observations. So for example, cell 3, 4 will tell you the absolute distance between the third and the fourth return. And now, actually, to make our entropy calculations the closest possible to a coin toss, let's select our threshold R as a percentile, an exclusive percentile that is, of all distances we have calculated, and input the percentile of 50%, or 0.5. And we can see that the median distance between any two returns is 0.4%. And now we can convert that into binary signals of coin tosses. If observations are closer or equal to the distance of 0.4%, our threshold distance R, we'll consider them close apart, the signal of 1, and if they are further apart, we'll consider them to be of signal 0. And now we can try and calculate those values, those binary signals, and convert them into our entropy calculations for dimensions that are greater than 1. And for that, we need to calculate vectors of consecutive returns of different dimensions. And for most financial applications of approximate entropy, you either choose your M, your embedding dimension, that is quite similar again to BDSL test in its definition. Most commonly, you just select M equals 2 or M equals 3. However, here, if we look at the formulaic expression of the approximate entropy test developed by Rukhin in 2000, by the way, the paper, as usual, will be available via our Google Drive, we can see that to check the approximate entropy for embedding dimension M, we have to also calculate the correlation integrals, that is, the proportions of observations that are within a particular distance for M plus 1 dimension as well. So if we want to test it for M equals 2 and M equals 3, we'll need our embedding dimensions and our dimensionality to be equal to 2, 3, and 4. And then we can calculate f of 2, f of 3, and f of 3 and f of 4, compare them together and calculate our approximate entropy. The logic of the calculation is that we try and mimic the logic of theoretical entropy by calculating the indicator function, which is basically equal to 1 if observations are close apart and 0 if they are far apart, and the distance would be the Chebyshev distance, so the maximum scalar differences between two vectors. Here we are concerned only with the Chebyshev distance and not with the Euclidean distance. It simplifies the calculations quite a bit, and it's quite conventional in the literature on approximate entropy in financial applications to use the Chebyshev distance. So here we calculate the frequency of how much or how often the observations are close apart. We divide it by the total number of observations in each column, and then we aggregate it across all columns or all rows. The matrix is symmetric, so it doesn't really matter. And here the logarithm is basically what allows us to approximate the entropy. And here the difference between those values of those aggregated correlation integrals between different embedding dimensions will allow us to proxy the approximate entropy. And then we can calculate what is the difference between our entropy that we observe in our data and the entropy that we would have observed if the data was perfectly random. That is the entropy of a coin toss. And we assume that our entropy would be equal to or smaller than the entropy of a coin toss, and that's why we selected that to be basically the 50th percentile, to make it as close to a coin toss theoretically as possible. And here we'll compare our approximate entropy that we would have calculated later to the natural logarithm of the number of states that we use to calculate our binary signals. And here, as we compare our real-world results to some ideal coin tosses, we would have the logarithm of 2, which is basically the entropy of a perfectly random coin toss. And what Rukhin in 2000 has proven is that this difference multiplied by 2 times sample size can be approximated using a chi-squared distribution with the number of the degrees of freedom equal to s to the power of n plus 1 and minus s to the power m. So basically we can use the well-behaved chi-squared distribution to test for the significance of the deviation of approximate entropy from a theoretical value for a purely random series. And this is the contribution of Rukhin in 2000, as this formal testing procedure was not available beforehand. So we'll be able to see with what probability our series is actually random, and whether we can assume that it is significantly different from a random coin toss, that is, and whether there exists any nonlinear dynamics or deterministic chaos in our quite short sample of stock returns. So without further ado, we've got to calculate the vectors of dimensions 2 all the way to 4, and here we can just refer to further observations in our sample. So here just refer to returns with a lead of 1, 2, and 3. Then we can just bottom right click it all the way down and remove the zeros in the bottom. And now we can calculate the distances, the Chebyshev distances between vectors. So now we'll treat those vectors, for example, as 2 separate observations, and we'll calculate the distance between the two as the maximum absolute differences between those scalar components. And the same would be true for example, vectors of dimension 4, like those 2 vectors. We'll just compare those differences and calculate the maximum absolute distance there. So, for example, for m equals 2, we can quite easily calculate the maximum absolute difference of, first of all, index from the first column, so this particular array, all the way to the penultimate observation because it's cut off over here. So, and we lock that and refer to the cell K45, and then we correspond to the observation in the second column over here, again locking columns and rows and referring to cell K45, and then we subtract the same vector. However, now instead of cell K45, the index would be determined by cell L44 with the row locked instead of the column, and we can copy it across over here as well. And we close the parentheses, enforce the formula, and enforce it for the whole matrix. And now we can calculate our correlation integrals based on the natural log of the proportion of distances that are within our threshold distance we have calculated earlier. So we can calculate the natural logarithm of count if how many observations in this column are less than or equal to the R parameter, the tolerance distance or the threshold distance, and then we divide by the count of elements in this particular column over here. And we can enforce this and again either drag it across or use Ctrl R, and then we can already calculate the f of 2, which is basically this aggregated parameter that then we'll use to calculate the approximate entropy. So that would be just the average of this particular row we have calculated. And this number doesn't tell you anything on its own. It's the comparison of f2 and f3, that is, those aggregated correlation integrals for different embedded dimensions, that tells us something about the entropy. So we have to move on and calculate the same parameter, the same variable for m equals 2 and m equals 3. However, here it will be quite easy. We can just copy this formula and paste it down to m equals 3 matrix. And here we can just tweak this formula to go from C2 to C40, because we cut off one more observation from the bottom, and here E2 to E40. And here we refer to cell K89 instead of cell K45. We can copy and substitute it over here, and then we can copy that, paste it over here, and instead of K89, we can select cell L88 with the row locked and substitute it over here. And again, enforcing it throughout. Please note that the dimensionality of the matrix is reduced because we are limiting the number of observations for vectors of increasing Ebeni dimensions. That's quite intuitive, and that's exactly what you can see over here as well. And what's important is that we can also calculate the correlation integrals by just calculating natural log. Again, count if of this array, count if those are less than or equal to the parameter r, and then divide by the count of the same array. We can just copy it across so we don't have to drag it. And again, dragging it across the whole row, and we can calculate the average across the whole row. And now we can calculate the approximate entropy based on the difference of f2 and f3, and that will give us the approximate entropy for the embedding dimension of 2. So f2 minus f3 gives us the approximate entropy of 0.61. Here we see that this is quite a bit lower than the theoretically expected approximate entropy for a purely random sequence. As you know, that would be the natural logarithm of 2, the logarithm of s, and that would be 0.69 approximately. But how significant this deviation is? To figure that out, we have to apply the chi-squared function developed by Rukhin, and code 2 times n, and n needs to be locked because it wouldn't differ from test to test. Then we multiply it by the difference between the theoretical entropy minus the observed entropy, and that is given us our chi-squared statistic. Now the degrees of freedom are just s to the power of m plus 1 minus s to the power m, and we know that our s is equal to 2, so we can refer to this particular cell, raise it to the power of m plus 1, so 2 plus 1, and subtract s raised to the power of 2, which is m, our embedding dimension. And we can see that the degrees of freedom for our chi-squared test is 4, so now we can calculate our p-value by using the right-tailed chi-squared distribution, inputting our value of the chi-squared statistic and the number of degrees of freedom over here, and we get a p-value of 12.52, which is quite high, quite a bit higher than the confidence threshold of 10%. So we can see that at the embedding dimension of 2, there are no nonlinear dependence or deterministic chaos observed for our dataset. But will that be preserved for higher embedding dimensions? Well, we are very close to figuring that out. We have to just calculate the Chebyshev distances again for m equals 4, so we can edit this formula, so just copy that across and edit it to have dimensionality 4. So here, again, we reduce the sample size by one observation, and then we refer to column F instead of column E, because we're now concerned with vectors of dimension 4. And instead of K89 here, we have to refer to cell K134, cell K132, and we copy it across as well over here. And then we can paste that as well and change the index. So when I will subtract, and here instead of K132, we refer to L131 with row locked instead of column again. And that will calculate our Chebyshev distances, again, the maximum distance between individual scalar components of our 4-dimensional vectors. And as usual, we can just calculate our correlation integrals, which are, again, natural logarithms, count if of those column elements less than or equal to, so within the threshold distance over here, r, and we divide it by count of the same array. And again, enforce it for the whole row. And here we can calculate, well, F3 we already know, it's minus 2.13, isn't it? We have calculated previously. And F4 is just the average of this particular row. And now we can calculate the approximate entropy for the embedding dimension of 3, so this minus that. We see that the approximate entropy is even lower, meaning that at the embedding dimension of 3, our data is more predictable than over here, with approximate entropy of 0.61. Will it be low enough for a significant result to emerge? Let's find out. We can actually just copy this formula across and see that our chi-squared statistic is now 21.21. And now we can calculate the number of degrees of freedom, which would be 2 to the power of embedded dimension plus 1, m plus 1, so 3 plus 1, minus the same parameter s raised to the power of 3. And we see that this particular statistic will be distributed as a chi-squared function with degrees of freedom 8. So now we can calculate the right-tailed chi-squared distribution with 21.21 test statistic x and degrees of freedom 8. And we can see that this p-value is actually very low, lower than 1%, signaling that there exists significant nonlinear dependence and deterministic chaos at the embedding dimension of 3. And that's all there is for testing for nonlinear dynamics and deterministic chaos in financial time series using approximate entropy. Please leave a like on this video if you found it helpful. In the comments below, make it to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.